Is that right?
Yeah. What'd you find out?
Seat?
So you're sign.
Seat.
Well, cue you in between parts.
Show me.
Sears.
Why do you think it was good?
Sears engine. Let's see. Sears. Okay, ladies, your turn. Michelle, what would you like to learn?
Since Michael was on, I'm going to start with H. Should be my car.
Is it tool checks?
I like him doing.
That's right. Okay.
Michael. No, what do you think?
Well, I'll bet. Whoever broke into my friend's party. Security guard told the police that he saw light come on. Sure. I'll bet this light comes on.
Boy, your turn. What would you like to learn? What is it?
All the ingredients.
You will go. No chance.
Let's just go with my I'd like to go over your house and check out what the police found that bubble so I can sign up on it. Or my housekeeper will let you.
Sorry, not quite. All right, your turn.
Yo. Oh.
Just
Sir,
Like that, a 4-way call.
if you could hear us, your mic is off and we can't hear anything. And furthermore, we can't really see anything at the moment.
Sir, excuse me, sir, can you hear us?
You can't hear me through that? You're muted.
I think all's well, Andy as well. His volume is muted, so he
Sir.
even if we turn on his
Wait,
speakers, he can't.
our speakers, huh?
Yeah.
Yes, everything is on here.
Sir, your mic is off.
Are we gonna mix it to the Jamaicans?
Your mic is off. We can't hear you.
Okay, no.
Let the lag wear off.
Should be hearing me now.
Right. Yeah. But we still can't
We
see.
still can't see
Let
the
me try
word
that.
either.
Okay. So it looks like that work here. Can't see the board?
No.
It's not work, man. It's low, so even
Oh,
that.
can you hear me?
I can hear you, but I can't see anything you have there.
It's cracking up as well.
Oh, they can hear me now, they can't see anything.
You're cracking
But
up.
it is being recorded, and there is video. Hopefully the video will come through soon. I suspect that.
Sir, we can see the video, but we can't make out what you have
Alright.
on the board.
Hey, can you hear us?
Extremely poor quality.
Yeah, like pixelated.
Right. So what we need to do is figure out and
This is foolishness.
what's the sum of all the openings across all those levels. So essentially I'm trying to. So what I like to
Mr. Core?
You still can't see what that works.
Your mic is muted again.
Yeah, you don't see.
Can you hear me now?
Yeah, we can hear you.
Okay. So whatever the base case is, that's what we need to equate the general form to find what D is. Because what we're saying is that I equals D at the bottom level. But in general, the input size is n minus I. So what we would know is that, let me be very explicit. When I equals D, I'm just going to just say this explicitly once. When I equals D, n minus I was equal to 0. All the relevant pieces are there. When we reach depth D, the general input size was equal to the base case value. That makes sense? That's the generality that persists no matter what equation you're solving. That's always the case. That's how you figure out what D is. So when you're at the depth, when I equals D, the general input size must equal your base case condition. Of course, in this case, this is a trivial, since I equals D, this is really saying that n minus D is 0. Which then tells us that D is actually n. So that's the systematic way you do this. Now, if you know D is n, then you can plug it in here to get an expression in terms of n alone. That's what you're after in the first place. So now you have T1 of n was 3D plus 1, which is really 3n plus 1. Is that clear? That's a very positive response. I like that. Are there any questions? Well, while you think about questions, and I prepare the next example, I'll just give Kevin another sweep of this board. Let's try another one. This one will be a little more interesting. Recall the second function that we obtained when we analyzed the second version of multiplication that we examined. You remember? We got if I write here, can you not see? Okay. So I'll just write it here then. All right. So got board is small, so I'm trying to maximize use of it. All right. So in our second analysis for multiplication, if you remember, we actually had a 3-case situation. And then I showed you how to reduce it to a 2-case scenario. Remember, let me just quickly review that. You remember, in fact, I'll write stuff again, just in case anybody missed it. So we had T2 of n was 1 if n was 0. I think it was it 3 or 4? I think it was 4 plus T2 n over 2 if n was even, and 4 plus T2 n minus 1 if n was odd. Remember that? And so what I pointed out to you is that in the worst case, you would have n being odd, because that's n minus 1 is a decrease that is a smaller decrease than halving n. So you can see that this will be decreasing slower. So if n is odd, then you get a slow decrease. It only decreases by 1. But the good news is that n minus 1 will have to be even. And once n minus 1 is even, then that means that the next time you reference the function itself, you'll be in the even case. And so the next time the input size changes, it will now become n minus 1 over 2. And so in the worst possible scenario, n would have to have some special value that starts out odd. And obviously when you subtract 1, you get even. But when you divide by 2, you get odd again. And then you subtract 1, you get even, and so on. It would force the calls, the recursive calls, or the self-references to alternate between the odd and even cases on every pass, right? And so what I said is that in those situations, we could then regard this pass as if it was 2 passes. In other words, it was always odd then even. And when we did that, we said, oh, so if it's always odd then even, then I might as well add these overheads together and just produce one single case to take care of those coupled situations when it was odd followed by even. And then I'll reduce my recurrence to 2 cases, which is then something that's easier to solve. So that's the first step. So in the worst case, I'll leave it as an exercise for you to figure out what kinds of values of n cause this behavior. And so then the resulting recurrence looks like this. It's 1 if n equals 0. It's 4 plus t of n minus 1, which then becomes 4 plus t of n minus 1 over 2 if n greater than 0. And we talk about in the worst case. In other words, n is odd. N is one of these magic values that causes this behavior. Like I said, I'll leave you to figure out what kinds of values those are. So when we simplify this, we get T2 of n is 1, n equals 0, 8 plus T2 of n minus 1 over 2 if n greater than 0. So now the question is, what kind of order of growth do we get from this? Well, we can draw a recursion tree again. Let's see what happens. Once again, I only have one T2 on the right-hand side, so each node is going to have one child. So this is a kind of degenerate tree. Instead of branching out, it has only one child. So it's essentially kind of like a linked list. My overhead is going to be 8. And the child node's size, input size, is n minus 1 over 2. Now I'll be at I equal 1. We'll continue with an overhead of 8 each time. And in the general case, what would it look like? Did I need more examples? Maybe I needed another one. But for you to hope to see any pattern. Yeah, let me, before I do the general one, let's put another one. Let's put another concrete one in. So the child node of the I equal 1 case looks like what? if you do this minus 1 all over 2, what do you get? You can try it on scrap paper. I hope you get n minus 3 over 4. No? You didn't get that? N minus 1 over 2. If you subtract 1 and then divide the whole thing by 2, subtracting 1 is subtracting 2 over 2, so that's n minus 1 minus 2, so n minus 3. The whole thing divided by 2, minus 3 over 4. Of course, anybody care to guess what this is going to look like? What does the input size look like after I step to it? N minus what? And it should be T2 because I left it. Thank you. That's an artifact from the old example. And minus 7 over 8 would be at I equal 3. What would it be in general case? Not I. All right, how does this denominator changing? Is it just plus 2 each time? Yeah, exactly. It's halving each time. So you're multiplying the denominator by 2 each time. Right? So at I equals 3, it turned to 8. I equals 4 will be 16 and so on. So by the time you get to some arbitrary level I, the denominator looks 2 raised to the I. And what's the numerator looking like? 1 less than this guy. Give Kim Hill a look peek. I hope this is working. But we can carry on and finish the tree. What does the leaf level say? So I'm going to call this level D. And what does that base case look like? 0, right? And what's its value? 1. So now, what I have is T2 of n is the sum from I equals what? Where do I start? 0. Where do I stop? I'm summing 8. This was 8 each time. Where do I stop? T minus 1. And I have an overhead of, well, the leaf value is 1. So I'm nearly done because you know that this is just 8D plus 1. The only challenge is to figure out what D is. So to find D, what am I going to solve? I need to solve the general case for the input size is equal to the leaf case, right? And remember in this case, that's when I equals D. So to find D, what I'll know is that n minus 2 to the D minus 1 divided by 2 to the D is equal to 0. Agreed? Okay, that's nice because that denominator goes away. That means that n is equal to 2 to the d minus 1, does it? But we want d. So what does that mean? So d. So this means that, okay, let's write it like this. 2 to d n plus 1. That tells us that d is log base 2 of n plus 1. So to finish it up, that means that T2 of n is 8 times log n plus 1 plus 1. Now remember what we said yesterday, the exact function is not important, or is not as important as the order of growth. So we're not going to get too hung up on the 8s and the log of n plus 1, etc., etc. What we really want to get at is, how does this function grow? What is the simplest function that would characterize for us how fast this function is growing? Log n. So this is theta log n. Questions? N minus 2 to the d. The question is, how did I get n minus 2 to the d minus 1 over 2 to the d? So why are we using I equals d? Because when you're at the leaf level, I is equal to d. That's how we define d. So if the general input size is always whatever I is, n minus 2 to the I minus 1 over 2 to the I, then when I equals d, the general input size will be n minus 2 to the d minus 1 over 2 to the d. And we happen to know that the reason is that leaf case is because that input is equal to the condition that makes it a leaf, which in this case was 0. Okay? Notice that if the recurrence had been defined so that this base case said when n equal 1 or something like that, we would have to plug that 1 in the equation instead of the 0. That would change what value of d you get a little bit. Yes? Worst case. WC stand for worst case. Any other questions? So now you are in a position to have a far more fundamental appreciation for the difference between the two algorithms. So if you remember, T1 was the time it needed to do mul1. And what was that doing? That was doing repeated addition. The second algorithm, mul2, used this when it's even, double and half, and when it's odd, then fall back to the just add. And what we're seeing is, I kind of gave you a kind of sort of informal reasoning why that one seems to be faster. Now you are seeing mathematically how much faster it is. The second algorithm has a performance or time complexity of on the order of log n. The first algorithm has a time complexity order n. It's gone. You have it in your notes. So the two are really, how does log n compare with n? Are they what about the same? Are they radically different? They're hugely different, right? If I had to draw a picture of what these functions might look like, here's n on the x-axis. So n might look something like so. Theta n is is linear, so it might look something maybe like, you don't know what constant there is. So generally, we'll be looking like this. Log n, regardless of whether it's 8 times log n or whatnot. Yeah, okay, so if it's 8 times log n, it might very well be higher on smaller values, but it pretty soon turns into a function that looks almost flat. It's always increasing, but it's increasing ever so slowly. This is, some constant times log n. Some constant times n. If you had a function if you had an order growth that was n squared, how would that look compared to these? It probably look something like that. I call that C3 times n squared. Don't pay attention too much to where they're crossing because it depends on what the values of those constants are. What's important is how rapidly they're increasing. And what you can see is that if n gets really, really large, log n is much, much, much smaller than any of these. To put it in numbers for you, and I'm working with log base 2 now. If I have n equals 16, what's log 16? 4. If n is 128, what's log 128? 7. Right there already, you're seeing 128, 7. Double it. 256, what's log of 256? Just 8. So I doubled n, and log n only increased by 1. Double it again to get 512, log of 512 is only 9. So by the time you get to 1024, the only log of 1024 is only 10. And by the time you get to 1,000 of those, so you get to about 1,000,000, log n is only 20, thereabouts. And by the time you get to 1 billion, log n is only 30. So that's a huge difference, right? What does that mean in concrete terms? If you're trying to solve a problem and you have one algorithm that can take log n time and a competing algorithm that can take order n time, they're not really competing. I need you to keep that in mind when you are solving your problem sets next week. All right? It's very pertinent to one of those problems, in fact, 2 of those problems next week. In general, though, from here to 4, going forward from here, you need to be very sensitive to that. I need for you to be aware of when you have an order n algorithm, when you have an order n log n algorithm, when you have an order log n algorithm, and how different they really are. And perhaps the most common kinds of comparisons you'll have to do is comparing things like log n versus n, or n versus n log n, or n log n versus n squared. Those comparisons come up a lot. It's important for you to have a very intuitive feel for just how much faster one is than the other. Okay? What I've done today is just shown you the method for arriving at these analyses. You're going to need a little practice to kind of get it honed. In due course, probably by the end of this week, moving into next week, we'll start talking about a high-power technique for doing a special subset of these problems that will enable you to get to these answers a little bit quicker. But I'm trying to give you all the techniques that you'll need in case whatever comes your way, you have a method for it. All right? So I'll see you on Friday.